What is the time complexity of multiplying two integers with n digits each? So this is a very basic computational problem. We learn how to multiply integers by hand very early, but from the point of view of algorithms, we can still ask how efficient that method is. So before we see a faster method, let's first analyze the standard multiplication algorithm. And so how does the standard multiplication algorithm works? So maybe we can start with a quick example here. So if we were to multiply, let's say 12 times 34, well, one way we could do this is we start by looking at the 4 and multiplying it by each. So let's say the number on the bottom right, we multiply it with all the numbers that appear on the top. So this will be 4 times 2, 8, 4 times 1, 4. Then we sort of do the same thing with the next number in the bottom, 3, but we shift everything once to the left. So 3 times 2 is equal to 6, and 3 times 1 is equal to 3. And then we sort of do these sums of what's above and below. So this was the multiplication. Now we sort of sum these. So we get an 8 here, 6 plus 4 is 10. So we carry a 1 here, and 3 plus 1 is 4. And we get 408, right? So in other words, if you're multiplying these two digits here, you put one of these numbers in the bottom, and then let's say your y0, which would be like the 4, you multiply it by each one of these. So you do these like n multiplications, and then you do that for each one of these, and then you add up the results, and that's how you get it, right? But what we want to know is like, so how many operations, or what is the cost of doing something like this, right? And so let me copy this so I can bring it for the next one. Let's leave it here. So the idea here is, and let's think of this more abstractly, if it was like some n-digit number and some n-digit number. So the idea is that to multiply these, for every digit on the bottom, and you have n of them, you have to multiply it with a digit on the top. So there's n digits on the bottom, and you multiply with n digits on the top. So just the multiplication step is around n squared multiplications. And then you need to add these results. Now notice that these results, so you're adding one by one. And how big can this be in terms of shifting? It can never be larger than n squared, right? So here it was 3, but at worst, you would get like a 9 here and a 1, and you carry it over, and you would have 4 additions. So it can't be worse than 4 additions, which is, again, n squared. And so the total complexity is going to be something like n squared plus n squared, but remember that big O ignores constants, so this is the complexity of multiplying two numbers when we use the standard multiplication, right? And then the natural question is, can we do better? Is there an algorithm that does better than this? And we're going to see that the answer is yes. And we'll learn one of these algorithms, and there are many of them that do better and better and better, but we're going to learn a simple one called Karatsuba multiplication, and which we will use divide and conquer to show how it's better than this order of n squared.